right? So it will be lots of multiplication. Let's do that in steps. First, a negated b negated by c, a negated b negated by c, then a negated b negated by c negated, a negated b negated by c negated. That's all in brackets. Yeah? Then d plus d negated. These old guys. Then now let's multiply these three. So we multiply a negated cd by b first, a negated b cd. Let me write it directly in this way. Then a negated b negated cd plus a negated b negated cd. And the last one, a by bcd, and then not space, a negated plus, multiplied by bcd. And then let's open brackets here. We'll get a negated b negated c d. Then this we multiplied this by this. Now we are going to multiply this by this one. So it's going to be a negated b negated c d negated. Now we multiply first this one by this one, and then this one by d negated, right? Plus a negated b negated c negated d plus a negated b negated c negated d negated. Now we just rewrite these guys. A negated b c d plus a negated b c d and b negated, yes, plus a b c d plus a negated b c d. Whoa, we did complicated the initial expression, right? But basically what we did, we created more or less a truth table of our initial expression. It's kinda, the standard form is kinda creating, when you make a standard form out of expression, you are kinda creating a truth table for that. Now you know that when one of these equals to 1, then the whole expression equals to 1. And you know that each of them specifies one case for every variable, like it is in the truth table. So let's do the truth table for that. So we have A, B, C, D, then our expression, I mean this one or the initial one, they are the same. And our cases are, there are going to be lots of cases. But what I suppose we can write down only the cases where the expression will equal to 1. So this will be cases 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, then 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1. Do we have twins here? Yeah, by the way, we have twins. This guy and this one, oops, and this one, they're exactly the same. So we can get, we have, is that the only one? We can get rid of this one. Yeah, as in the last example. Do you have any other twins? Oh yeah, we have this one and this one. Yeah, we should have looked for equal products beforehand. Yeah. Any more of them? I don't see any more of them. But Now the point is that every one of these terms represent one line of truth table. So, okay, what the hell, let's write down the whole truth table. 0, 0, it's going to take time. And so this is the mega huge truth table for this expression, yeah. And we know that this expression will equal to 1 in cases that we've written down here, and we have one case for one product, and this is nice. So we have 0, 0, 1, 1, 0, 0, 1, 1 here. We write 1, then 0, 0, 1, 0, 0, 0, 1, 0 is this one, 1, then all zeros 1, it's this one, then all zeros, then 0, all ones, then all ones down there, down here, and all others will be zeros here. And one more. So this is the truth table for this expression, and this one is the initial expression, right? And the initial expression that we had previously in some videos before about De Morgan's theorem was this one. So I remind you that we took this expression, we applied some De Morgan's law on that, we get this one, and now what we did, we put this sum of products term form, right, into canonical or standard sum of products form, right? And I was claiming that this is somehow nicer form of representing truth table. Yeah, you see how huge and ugly is our truth table. Yeah, I even needed to zoom out to see it, and how nice is the canonical or standard sum of products form comparing to the truth table. And they have exactly the same meaning. They have one line or one product in case of sum of products term that represent one case, and in case of standard sum of products term we have only cases that represents one as the result of the expression, and all others, which you don't see of course, are zeros. So green ones, every green one in the truth table represent one product in the standard sum of products term. And very often we use a standard form instead of writing the truth table. Or the other thing could be is we can get a canonical form out of truth table, right? We can do lots of things. So what we did, we had some random expression, very ugly, yeah, and we did a lot of stuff with it, right? We De Morganed it, right? We multiplied it by ones, and in the end we get this nice standard form. Yeah. But the other thing, and I just showed you the truth table just to prove this point. And the other way is to have the initial expression, right? And just do a truth table on that to write this expression right here, yeah, and then calculate for each case the result of this expression, and you will get exactly the same table as here. And then out of this table you could take every case with ones and create canonical form for that. So for example, you have some kind of truth table. It makes it super easy to create a canonical form expression out of truth table. You just write for each line, you write A, B, C, D, and then if they're all zeros you negate each one of them. And then for this one it will be A, B, C, D, and all negated except D, because D is 1. D is already 1, you don't need to negate it. And then 0, A, B, C, D, here you negate all except C, and the last one, A, B, C, D, you negate these two and don't negate this one. Then the same here, A, B, C, D, you negate A, only A, and then A, B, C, D, and you don't negate anything for the last one. And that's how you can get a canonical form expression. You just need to sum it. Yeah, and now you get a canonical standard or canonical. These are exactly the same. They have exactly the same meaning. So this is what you can do. And as I said before, don't be confused with why the hell would we need to complicate our expressions. Yeah, this is a very universal form. You can directly go from this form to truth table, you can directly go from truth table to this form, and you even can go directly from this form to kernel map, and you can do, so it's basically, we can sum up, have a little summary that kernel map, truth table, and standard sum of products forms are some kind of equal ways to represent an expression in its full grace. Right, so that's it for now. Let's move on.